ठीक है, vanadium reacting with Fe3 plus.
I tried it.
ठीक है, so what was the end result like if I open the data booklet? Did you figure it out?
I got like the final equation being 3V plus 2Fe3 plus into 3V2 plus 2Fe.
V2 plus 3V2 plus, right? I mean, what was the
Yes,
final V? Okay, I get it. So okay, so what you did was, where are the equations? This one, right? So remember, it's Fe3 plus, right? So with Fe3 plus, I'm going to write down all possible electrode reactions for Fe3 plus. One second. So Fe3 plus, all possible electrode reactions that involve these two. So I'm going to pick those and I'm going to paste it over here. So these are the possible reactions that Fe3 plus will undergo. And we've got vanadium. So I'm going to pick all possible reactions involving vanadium. So if you go and have a look, the vanadium, there's only one equation, which is this one. It's V2 plus. He gets this one. That's the only one that has vanadium in it, right? So vanadium and Fe3 plus. So these are the only reactions I found, vanadium and Fe3 plus. So we're gonna try and figure out who's going to gain electrons. The higher potential, right, is the one that gains electrons. So that's going to be this one, right? And we do have Fe3 plus, so that means Fe3 plus is the one that gains electrons, right? So I found so what I found my higher potential, the one that gains electrons, right? So that's this one. So that's my high E naught. And the lower one is the one that's going to lose electrons. So who's going to lose electrons? It's going to be V, right? So that's the one that's going to lose electrons. And I do have V. So vanadium, that's one of my reactants. So that's fine. Nothing wrong with that. So that's my lower E naught. That's the one that's going to lose electrons. And I'm going to select that. Okay, so that's my lower E naught. And I'm going to make the overall reaction. So I'm going to multiply this by 2 so that the electrons gained and lost are equal. I'm going to add up the reactants. So the reactants are what? 2Fe3 plus. And the other reactant is vanadium. And what are my products? The products are, okay, so the products are 2Fe2 plus vanadium 2 plus, right? So so the E naught cell for this is going to be the reduction potential minus oxidation potential is 0.77 minus 1.2. And what do I get for this? It's what am I getting? That's 1.97. Okay, so it's a very so it's a very feasible reaction. Is this clear? Is this clear, this part?
yes, sir.
Okay, so that's a very feasible reaction. So what do I have in my solution after the reaction? So after the reaction, so after step number one, this is step number one, and this is my equation for step number one. So after this reaction, what I have left in my solution is I've got the two products, which are Fe2 plus, and I've got V2 plus, right? So these are the things that are produced. And then there is excess Fe3 plus. So that means there must be some Fe3 plus that will still be left in the reaction. Is that clear?
Yes, sir.
So there must be some excess Fe3 plus that will be. So what I'm going to do is I'm going to try and figure out whether there's going to be a further reaction or not, especially with V2 plus. Okay, remember it's not going to get oxidized in one step. So will there be a further reaction or not? So I've got Fe2 plus, I've got Fe3 plus, so I'm going to copy their reactions. Okay, so I've got Fe2 plus and Fe3 plus. So let's pick that. And remember, I've got V2 plus now. So I'm going to see what happens to V2 plus. There are multiple options for V2 plus. There's V2 plus over here and over here. So there are two reactions, two electrode reactions where V2 plus is involved. So there are two possible things that could happen to V2 plus. So I've copied these. So again, it's the higher potential that gains electrons. So that clearly is the Fe3 plus one. So that is the one that gains electrons. So that's my high E naught, and it's gaining electrons. So so this is the one. And the lower E naught is the one that's going to lose electrons. Who's the lower E naught? Well, the lowest E naught at the moment is minus 1.2, but I don't have any vanadium left. I mean, if you look at my reactants, there's no vanadium. Which is the next lowest E naught? That's minus 0.44, but I don't have any iron. So yeah, I'm going to get rid of that. There's no iron. So it's not going to lose electrons. Then after that, who's the lowest E naught? That's V2 plus, and I do have V2 plus. So that means that's the one that's going to lose electrons, right? So that is my lowest E naught. And I'm going to write down what the reaction is going to be between these two. So what happens now is Fe3 plus is the one that's my reactant, and in the other one, the reactant is V2 plus. And what are my products? My products in the first one is Fe2 plus. The electrons are already balanced, so I'm not going to do anything. And the product in the next one is V3 plus. Okay, so I've found this reaction, and I can calculate the E naught cell for this reaction, which is positive reduction potential minus oxidation potential. That's 0.77 minus 0.26. And that gives me what? What do I get out for this? 1.03. Can somebody double check this? Okay, but is this part clear?
Yes, sir. Also, I double checked it. It is 1.03.
Okay, so after the first reaction, I had V2 plus, but then that V2 plus got further oxidized to V3 plus. So what do I have in my solution after the second reaction? Well, V3 plus is formed. There's Fe2 plus, and there is excess Fe3 plus. So there's definitely going to be some excess Fe3 plus because that was an excess. So now I'm going to figure out whether there's going to be a further reaction or not. So I'm just going to copy these equations. For iron, they're already there. Now I'm going to look for equations for V3 plus. What can V3 plus turn into? So if I go back and have a look, now there's V3 plus involved in these two. So there are two reactions that involve electrode reactions that involve V3 plus. So let's find out what's going to happen in this. Again, highest potential is 0.77, so that's the one that's going to gain electrons. Nothing wrong with that. We've got Fe3 plus, so that is the one that gains electrons, right? So that's my highest E naught. And the lowest E naught is the one that loses electrons. So the lowest E naught in this case is at the moment it's minus 0.44, but there's no iron, so it won't lose electrons. Which is the next lowest? That's minus 0.26, which is there's no V2 plus as well. I've got V3 plus over here, but I don't have any V2 plus, so I'm going to reject that. Which is the next lowest? That's the other iron equation. Again, I don't have Fe, so how it won't lose electrons. So the one remaining equation, the lowest one is going to be this one, right? And I do have V3 plus. So I figured out that this is the equation that's going to lose electrons, right? And that's going to be my lowest E naught. Is that clear? So highest E naught gains electrons, lowest, and I'm going to write down the reaction. The electrons are already balanced. My reactant is what? Fe3 plus. And the reactant in the other equation is V3 plus H2O. I say, and what are my products? My products are, okay, so my products are Fe2 plus. And in the other equation, the products are VO2 plus 2H plus. Is that clear? Okay, so is this part clear that there's another reaction now?
Yes, sir.
Okay, so that's my reaction. And it still continues, right? Because I've got further equations. So now you've got three reactions. The first one happened, V got converted to V2 plus, then V2 plus got converted to V3 plus, then V3 plus got converted to VO2 plus, right? So now I'm going to try and figure out what happens after this. So what do I have after this reaction in my solution? It's going to have Fe2 plus. It's going to have VO2 plus. Well, there is some H plus ions as well if somebody needs that. It's plus I've got excess Fe3 plus. Remember, Fe3 plus was in excess. So will there be another reaction after this? So for iron, I'm just going to pick those equations already. So I'll just copy paste those. And for VO2 plus, I'm going to look for it's VO with a charge of 2 plus, right? So VO with a charge of 2 plus, there are two equations. Let's see, will there be a further reaction after this or not? So, so let's try and figure out whether there's going to be a reaction between VO2 plus and Fe3 plus. Now, if you look at this, who's got the highest potential? It's this one, right? But we don't have VO2 with a charge of plus one. We don't have that. So that is not the one that's going to gain electrons. So by default, it's going to be the other one, which is 0.77. That's the one that's going to gain electrons, right? Is this clear that Fe3 plus is again gaining electrons? Is this clear?
Yes, sir.
Yes.
Yes, sir.
I said, who's going to lose electrons? The lowest one, which is minus 0.44. We don't have Fe, so it's not going to lose electrons. Minus 0.04, that's the lowest. We don't have Fe, it's not going to lose electrons. TK. 0.34, we don't have any V3 plus anymore, so that it's not going to lose electrons. So who's going to lose electrons? The only one that's left is 0.77 back again, right? I mean, I'm stuck at 0.77 now. So Fe3 plus was losing electrons, and we are coming back to this equation. That means it's not going to be there's not going to be a further reaction because the reaction that I chose as the highest one, it's also the one that's the lowest one, right? Do you get the point? So that means there won't be any further reaction because you're coming back to the same reaction. So is this clear that the highest one and the lowest one are coming out to be the same
Sir,
reaction?
why can't we choose VO2 plus for
Mm.
the as the highest?
So we can do that. I mean, let's assume I'm not going to pick this, TK. Let's assume that lowest, right? Let's assume we don't have, I mean, we actually do have Fe2 plus, right? Nee, why would I choose one? Lowest is 0.77.
Like, why wouldn't you choose VO2 plus for the as the highest and then Fe3 plus like
नहीं
Fe?
we don't have this ये तो नहीं है हमारे पास
Okay.
I mean there's a difference between this and this, right?
Yes.
This is VO2 with a charge of plus one. So remember, you're coming back to when you're trying to select the lowest one, you're coming back to the same equation, okay? So that means nothing will happen, right? Is that clear? So
Yes.
you're stuck. The highest one is the same, and the lowest one is also the same. So that means that's it. Okay, there's nothing, no further reaction, and so that's it. So this working was irrelevant, right? So you had three reactions, and those were your three reactions. What I'm going to do now is I'm just going to add up the three reactions. There were three steps that were happening. Okay, remember you actually got this question in one of the papers where you had to do all of this. So remember the ones that have multiple oxidation states, okay, reactions that involve multiple oxidation states, they tend to be more problematic because you have to look for the fact that they will have further reactions. So vanadium is one of those things. So what I'm going to do is I'm going to pick all three reactions now, which I've done, and I'm going to add them up, and I'm going to try and figure out what my overall reaction now is. So let's try and figure out what the overall reaction is. So in this case, what am I getting? It's if I add everything up, it's going to be 4Fe3 plus. Things that appear on both sides, they will get cancelled out. So what's getting cancelled out? V2 plus gets cancelled out. V3 plus gets cancelled out. I guess that's it. Um, plus V plus H2O. And the product that's going to be it's going to be 4Fe2 plus VO2 plus charge and plus 2H plus 1. Okay, that's my final reaction, which I got. Okay, is this clear?
Yes, sir. Yes, sir.
Okay, I said normally you don't get this question. Normally the questions that you're going to get are going to be pretty simple. I mean, like this, it's just simple, one step. Okay. Most of the equations over here, they are going to be one-step reactions. That's it. They don't have I mean, elements don't have a lot of oxidation states. The only thing you're going to watch out for is vanadium. Vanadium has a lot of reactions. Okay. I mean, for example, zinc. For zinc, you don't have to worry about whether zinc is going to get further oxidized or not because it won't. That's it. Zn2 plus will get formed, and that's about it. So for most reactions, you're not going to do this. Uh, for there's another one over here like Mn, right? That will have a similar problem as well. I'm going to do it over here. Okay. So remember, I'm not going to waste time copying the equation. So I'm going to try and figure this out over here. So let's have I have a reaction where Fe2 plus reacts with MnO4 minus 1 acidified. So if you look over here, where is Fe2 plus? Okay, it's in one screen. So I've got Fe2 plus in this equation. I've got Fe2 plus in this equation, and that's it. And I've got MnO4 minus 1 over here and over here. And since it's acidified, so I'm not going to pick I mean, I can think of this one as well. Um, so I've got these three reactions. So remember, higher potential gains electrons, lower potential loses electrons. So let me highlight the potentials. This is 0.41. So I've got, okay, minus, what are the potentials? It's 0.44 minus and 0.77. And over here, I've got 1.56, 1.67, 1.52. Which one is the highest potential? That's probably this one, right? So that's the one that gains electrons, right? So MnO4 acidified is the one that's gaining electrons, and that's fine. There's nothing wrong with that. I do have MnO4 minus one, and I also have H plus one, right? Is that clear?
Yes, sir.
And then the lowest one is the one that loses electrons. The lowest one is? which one? It's I mean it's minus 0.44, but I'm not going to pick that because I don't have iron. So that's not the lowest one. Uh 0.56 is the lowest one, but I'm not going to pick that because I don't have this. So which one is the lowest? That's Fe2 plus. That's the one that's the lowest one. So that's the one that's going to lose electrons. Okay, so that's my lowest. So remember, you're going to do all the working like this on the where the electrode reactions are written. Now what you have over here is, okay, I'm going to write down the first reaction. Uh, the iron equation has to be multiplied by, let me highlight the whole equation. So it's this equation versus this one. So I'm going to add up the two reactions. The iron equation has to be multiplied by 3 so that the electrons are balanced. So it's going to be what? 3Fe2 plus. And so that's my reactant. In the other equation, the reactant is MnO4 minus 1 plus 4H plus 1, right? And the product is 3Fe3 plus. And in the other one, the product is what? MnO2 plus 2H2O. Now try doing this directly. Will there be a further reaction or not? Okay. See, Fe is the one that's losing electrons, right? It's the lowest potential, right? MnO4 is the one that gained electrons and turned into MnO2. Will MnO2 gain electrons again? Is it still the highest potential? I mean, look at MnO2. I mean, you got MnO2 now, right? So that was step number one. It's the highest potential. It was gaining electrons. You ended up with MnO2. Will MnO2 gain electrons again? It's still the highest potential compared to Fe over there. So that means it is still going to gain electrons. Is this clear?
Yes, sir.
Okay, I'm just trying to do this directly now right, without copying too many equations. So first step, Fe lost electrons because it was the lowest potential. MnO4 gained electrons, became MnO2. But MnO2 will gain electrons again because it's still the highest potential. It will become Mn2 plus. Will Mn2 plus gain electrons? Will this Mn2 plus gain electrons? Fe is losing electrons. No, it won't because it's the lowest potential. Lowest potential does not gain electrons. So that means the reaction will stop at Mn2 plus. Is that clear? I mean, it's not going to go further because when you come to Mn2 plus, it's minus 1.18 volts. That's not going to be the highest potential. It's not going to be higher than this. So that means it's not going to gain electrons. So is this clear, this part? So I would have to make another equation now. TK with because now I have a second reaction after this one where so this time I would have to multiply the Fe equation by 2. So this reaction I would have to multiply the Fe equation by 2. And so what happens now is that it's 2 Fe2 plus reacting with MnO2 plus 4H plus 1. And the product is going to be what? It's going to be 2Fe2 plus. So 2Fe3 plus. And it's going to be Mn2 plus and 2H2O. Okay, so Fe will further react with MnO2 and this is the reaction. And there's not going to be any further reaction. And then you have to make the overall equation. So you're going to add up everything. The MnO2 will get cancelled out because it's on both sides. You're going to have 5 Fe2 plus and an MnO4 minus 1, and you're going to have 8 H plus 1 ions, and you'll have your products, which are 5 Fe3 plus and 1 Mn2 plus and 4 H2Os. right? Is that clear? Is this clear to everyone?
Yes, sir.
So that's the final reaction. For this one, because it's a very common reaction, just make sure how to do this one. The shortcut to this one is, I mean, there's a shortcut to this one. The shortcut is like without going into too much detail, if you want to figure out what the reaction is between iron ions and MnO4 minus one, don't pick any of these two equations. The shortcut is, or the trick is, just go for this equation, the other one, this one over here, the 1.52 volts. Okay, go for the, I mean, this is the shortcut. Like if you ever have to avoid the details, because in this reaction, the MnO4 gets converted to Mn2 plus directly. So even though this is not the highest potential, I mean, the reaction happens in two steps. It first forms MnO2, then that MnO2 gets converted to Mn2 plus. But the end result is it is forming Mn2 plus, right? So the shortcut for this, because it's a very common reaction, comes in a lot of questions. There's a lot of it comes in a lot of places. Iron ions with MnO4, that's your typical uh redox titration. So you can make a point, and that is that you just go for the for this equation over here. Even though it's not the highest potential, but go for this one. You'll end up with this equation, the final equation. Okay, is this clear? This one?
Yes, sir.
Okay, so we're kind of done with equations, right? So remember, most of them are going to be simple. They're not going to be that complicated. Most of them, but they are going to be complicated cases. A lot of them would be very, I mean, like let me show you questions 1 second. Okay, let me show you the older one first. So, for example, the KINS208 reaction, right? Or what's going to happen over here? So, so simple, right? It's K plus one. So it's simple. It's K plus one, I minus one, and S2O2 minus. That's it. And you have to figure out the reaction. They don't have multiple oxidation states, so you don't have to do the stuff that you were just doing. There's just three reactions: K plus one gaining electrons to form K. That's I think minus 2.92 volts. There's I minus one iodine plus two electrons and forming two I minus one, and that's 0.54 volts. There is S2OA 2 minus, gaining two electrons to form two SO4 2 minus, and that's 2.01 volts, right? So most reactions are just going to be simple. No multiple oxidation states, nothing. So who's going to gain electrons? The highest is going to gain electrons, which is S208. So that's fine. We do have S208. Who's going to lose electrons? K is the one that's going to lose electrons, but we don't have any K. So who's going to lose electrons now? It's going to be I minus one. We do have I minus one, so it's these two equations, and that's it. The electrons are already balanced. You add up the reactants, 2I minus one, the other one S2A 2 minus, right? And then you have your products, which are what? Iodine and 2SO4 2 minus. Okay, so that's it. No multiple. You don't have to worry about whether there's going to be a further reaction or not. No, there's not going to be any further reaction because that's about it. Okay, with sulfur, you don't have a lot of equations. Is this clear?
Yes,
Okay.
sir.
So moving on now. What we're going to do is we're going to do or talk about non-standard potentials. अच्छा, what are non-standard electrode potentials? So, and what happens in non-standard electrode potentials? What happens in non-standard electrode potentials is that your normal electrode potentials like Cl2 plus 2 electrons, this is E naught and that's given as 1.36 volts. That's calculated in standard conditions. The concentration of the solution is 1 mole per dm cube. The temperature is 298 kelvins or room temperature. The pressure is 1 atmosphere. Now, this is an equilibrium reaction, which means that the equilibrium can shift. It can shift forward or backward. So it can shift in either direction, forward or backward. Now, let's say I increase pressure. So remember Lee Shatler principle, the rules where would the equilibrium shift? How do you predict? So if I increase pressure, would it favor less gas or more gas? Which side will the equilibrium shift? Anyone?
Left.
No, when you increase pressure, less gas or more gas?
Less cash is most competitive.
So which side has less gas? More side. That's the right side, right?
Right.
ठीक है. अच्छा, so the equilibrium is going to shift if you change any conditions. ठीक है, you change concentration, you change pressure, you change temperature, it's going to shift. So let's say you increase pressure, it's going to shift towards the less gas mode side. Will your electrode have more electrons or less electrons? I mean, your platinum electrode, will it have more electrons or less electrons? I mean, chlorine is going to gain, equilibrium shifts to the right, right? What happens? Cl2 starts to gain electrons, right? So your platinum electrode will become more electron deficient. Is that clear?
Yes, sir.
It becomes even more electron deficient, uh, or more positive, because chlorine is going to consume a lot of electrons. So the platinum electrode, well, what did the electrode look like? वो था ना कि when we did the drawings, right? We did this chlorine electrode as well. Yeah, this one. So if chlorine will start gaining electrons, a lot more electrons, right? If the equilibrium starts shifting forward, right? And if it starts to gain electrons, so it's going to gain a lot of electrons from the platinum electrode, and the platinum electrode will become more positive. So that means that your potential is no longer going to be 1.36. It's going to be higher. Maybe, I mean, it's just a hypothetical value. Maybe it's going to become 1.45 volts. So more positive. It's going to become more positive because the equilibrium is shifting to the right. So the rule is that whatever you do, if there's a shift to the right, which means that they start gaining electrons, then your electrode will become more positive. And if the shift happens towards the left, then that means that it's going to become more negative. ठीक है? Is this clear?
Yes, sir.
So this is what's going to happen. ठीक है? अच्छा, now the thing is that so that's it. So just predict okay, what's going to happen in these cases. Okay, if I have Fe3 plus electrons and it's in equilibrium, under standard conditions, and it's in equilibrium with Fe2 plus. The electrode potential has a value of 0.77 volts. Actually, if the concentration of Fe3 plus is like very low compared to the standard conditions, and if the concentration of Fe2 plus is very high, where do you think will the equilibrium shift? Left or right?
इसमें क्या किया?
Yeah, when I've changed the concentrations now, so where would the equilibrium shift? Compared,
Left.
compared to the standard conditions, I've decreased concentration, so equilibrium will try to,
Shift left सही है.
TK will try to shift left. What will happen to the potential? Higher or lower?
अब और lower हो जाएगा.
ठीक है, so maybe it becomes 0.65 volts. ठीक है. अच्छा, remember, so it's not going to be a huge difference. ठीक है, because you're not going to change the nature of the element a lot. ठीक है, so if it's like if it likes to lose electrons, it will still like to lose electrons, but it will like to lose electrons slightly more. So the potential difference or the change in potential that's going to happen, that's going to be it's going to be very, very little, not going to be huge. Similarly, if I have Acha, now in this case, is this clear? Zainab, Jude, is this clear?
Yes, sir.
Okay, so the next thing is you can even you can measure or estimate a value for this non-standard potential, and that is done by using a Nernst equation. That equation, it's an equation. You're just going to use this equation to estimate the value. I mean this value over here, I just made it up, right? It's not going to be 0.765. I'm just saying that what I wanted to state was that it's going to be lower, right? So I can measure exactly what the value is going to be. So to measure the non-standard potential, you're going to take the standard potential. You'll have 0.059, that's a constant, divided by the number of electrons that are in the equation, which in this case is 1. So divide that by the number of electrons. Then log of the oxidized species over the reduced species. Okay, that's your equation. Oxide species is the left-hand side one. Its concentration. Reduced species is the one that's on the right side. So you've got two species, one Fe3 plus, the other one is Fe2 plus. So the one that appears on the left side, that's your oxide species. The one that's appearing on the right side, that's known as your reduced species. So we're going to try and figure out. So E naught was what? It was 0.77. The standard potential was 0.77. Then you have 0.059. Remember, Z is the number of electrons, which in this case is 1. So that absolutely makes no difference. So that's 1. And then there is log. TK, remember base 10 log. TK, it's a button on your calculator for the moment. So log of oxide species concentration, so that's 0.05 divided by the reduced species concentration, which is 1.2 given above. So can you try and tell me what the value is? Kya hai, Ibrahim? Zaina, what are we getting for this?
0.69 आ रहा है मेरा दोस्त।
ठीक है 0.69 volts, right? So you're getting 0.6. So basically, my 0.65 was like a rough estimate. It's actually coming out to be 0.69 volts. So that's it. So basically, if you know the concentration of both sides of the reactant as well as the product, and this only works for concentration. So there, I mean, this is the only Nernst equation. There are many different versions of the Nernst equation. This is the only one that you have to remember. So so remember this, and you'll be able to figure out the non-standard potentials. So remember that the equilibriums are going to shift if you use non-standard conditions. Okay, so if I increase the concentration of I minus one, the equilibrium will shift backwards. If it shifts backwards, it's going to become lower. If I decrease the concentration of I minus one, the equilibrium will shift forward and it will become more positive, right? So remember, if it shifts forward, it becomes more positive. If it shifts to the left, it becomes more negative. Is that clear?
Yes, sir.
Or इसमें ना the
Yes, sir.
one thing that you have to remember is that for solids the concentration is going to be taken as one, as a constant. ठीक है. So let's continue tomorrow then. ठीक है, we'll continue tomorrow.
Yes, I love this.
Okay, take care. Love.
Obviously.